What if an AI could make your GPU 21 times faster while you sleep? GPU programming is brutally hard. Memory hierarchies, thread scheduling, hardware architecture, most developers never unlock more than 50% of their GPU's potential. Enter AutoKernel, an autonomous AI agent that optimizes GPU kernels through pure experimentation. It modifies code, benchmarks it, keeps what's faster, reverts what's slower. 225 experiments across 4 campaigns. 0 humans needed. Our target? The NVIDIA RTX 5090 Blackwell, 209.5 teraflops dense FP16, 1676 teraflops FP4 sparse peak, 32 gigabytes of GDDR7 memory. The mission? Accelerate a 35 billion parameter language model using W4A16 quantization, 4-bit weights, 16-bit activations. The frontier of efficient inference. Starting from a naive baseline of just 15 teraflops, here's the optimization curve. Each dot is an experiment. Green means kept, gray means reverted. Watch the line climb. First, auto-tuning with L2 cache swizzling. 22 configurations tested, tile indices reordered for cache locality. Instantly jumped to 137 teraflops. 9 times faster than baseline. Second, persistent kernels. 680 long-running programs instead of 10,000 short-lived blocks. Better L2 reuse. 0 launch overhead. 156 teraflops. Third, the flat K loop. Replacing nested loops with a single flat iteration, the GPU loves simple, predictable code. 170 teraflops. Fourth, compile time constants. Runtime division replaced with lightning-fast bit shifts. 178 teraflops. Then came the paradigm shift. Don't compete with kublas. Optimize what's unique. Split the dequantization into a fast Triton kernel, then hand the FP16 tensor to kublas for the Matmul. 196 teraflops. FP16 accumulation was the game changer. One tiny change, using FP16 output instead of FP32, accessed the FP8 MMA pathway. 290 teraflops. That's 157% of the dense FP16 peak. A single line of code nearly doubled throughput. Triton 3.6 was the final breakthrough. Smarter shared memory management unlocked larger tile sizes. 328 teraflops. Here's the full W4A16 optimization path. Every labeled milestone on this chart was an autonomous discovery, 21.7 times faster than where we started. But we were just getting started. Campaign 2, NVFP4 FP4 Matrix Multiply. CUDA C++ quantization kernels replaced Python 15 to 52 times faster. The result? 1,261 teraflops. 75% of the theoretical FP4 peak. Campaign 3, Production Serving with VLLM. 31 experiments tuning chunk prefill. Sequence limits, GPU utilization, baseline 91 tokens per second, optimized 122, 34% faster with just configuration changes. Then speculative decoding with DFlash, 75 experiments and 14 patches to VLLM. Here's where it gets interesting. Performance is non-monotonic. Draft equals 6 gives 170 tokens per second. Draft equals 5, only 114, 48% slower. Not algorithmic. CUDA graph capture size alignment on SM120. Never extrapolate, always measure. Campaign 4 revealed the hidden bottleneck. Everyone optimizes KB cache for batch throughput. But on hybrid architectures like Quan with Mamba layers, the Mamba state at 50.3 megabytes per request is what actually gates scaling. FP8 KB cache didn't help, but having Mamba state to FP16, 8,245 tokens per second at 128 concurrent users, a new RTX 5090 record to a T, at concurrent users, a new RTX 5090 record users. Along the way, we discovered 15 bugs across 3 major frameworks, 7 in VLLM, including an MTP batch crash that took 20 debug experiments, 3 in SGL-Lang where NVFP4 showed 100% token acceptance because all output was garbage, and 3 in Flash and Fear with hard-coded CUDA paths. Without rigorous benchmarking, these bugs would have shipped to production. The cost story is remarkable. An RTX 5090 costs $2,000 one time. At 170 tokens per second, that's 8.5 times more cost-effective than an A100 at $15,000 per month in the cloud. Payback period, 1 month. Here's the most surprising finding. 44% of expert intuition was wrong. Out of 225 experiments, 88 were reverted because they made things slower. Half of all hypothesis-driven optimizations failed. Without the keep or revert discipline, 39% of changes would have silently degraded production performance. 4 key insights from the full campaign. 1. Correctness first. 100% acceptance rate is a red flag, not a success metric. 2. Pragmatism beats purity. Split concerns and delegate what libraries do better. 3. Hybrid architectures shift bottlenecks. Mamba state, not KV cache. Gates batch throughput. 4. Measure everything. Performance can be non-monotonic for reasons that have nothing to do with your algorithm. Here's the complete picture. All 4 campaigns, all 225 experiments on a single dashboard. W4A16 Matmul, NVFP4 Matmul, single-user decode speed, and multi-user batch throughput. AutoKernel, autonomous GPU optimization while you sleep.